Hi, Hayden. Ms. Townsend here. We're going to answer this question, but first I want to make sure that you actually understand the concept. So let's go over it. The problem statement says, let's find a basis for the indicated subspace of R3, and the subspace that's given to us is the plane with this equation. One thing that I want you to notice is that when x, y, and z are all equal to 0, we get 0. So this is a plane that passes through the origin. We also know that the normal vector of this plane is given by the coefficients of x, y, and z here. So there's an implied 1 there. So the normal vector of this plane is a vector with components 1, -2, and 5. Now, from the screenshots that you sent me, it looks like you guys are using slightly different notation. This is the notation that we use for vectors in Calculus 3, but in your textbook, it looks like you're looking at row vectors, which I think is a little unusual, but they're using parentheses rather than these brackets in your textbook. So this is the normal vector to that plane. So they want a basis for this. Basically, they want the right number of vectors, and they want like several vectors that you could multiply by constants and add together to get this plane. That's what a basis is. So let's look at the definition. In your textbook, it says a basis is a finite set S of vectors in a vector space V, and that finite set is called a basis for V, in our case, a basis for this plane, provided that the vectors in S are linearly independent and the vectors in S span V. And when I say that the vectors in S span V, that just means I can take one vector, multiply it by a constant, and then add the other vector, multiply by a constant. And then for all of the different values of that constant, those two constants, if we do that, we'll get the plane. We're going to get this plane right here. And then we also have to understand what linear independence is. So I'm going to have to assume some things about what you already know. But let's just look at a couple of examples. Let's say that, let's talk about span first. So let's say that you've got a vector u, and it's written this way. Let's say we're just in the plane for right now. So if we want to draw that vector in standard position, we'll start at the origin. We'll go 1 unit in the x direction and 2 units in the y direction. And that's where the terminal point of that vector will be if we start at the origin. So that's the vector u. Now the span of u is just going to be the set of all vectors v, such that v is just equal to any constant times u. And in this context, we're going to assume that that constant is just a real number. Now, if I just took u and multiplied by 1, I would get this vector. If I take u and I multiply by 1/2, well, I'll get this vector. If I multiply it by 2 times u, multiply component by component, we're going to get the vector 2, 4. So we're going to go 2 units in the x direction and then 4 units in the y direction. That's 2u right there. So there's half of u, there's u, there's 1.5 times u, there's 2 times u. And as we take different values for that constant, this value, that constant c, as we take different values for that constant between 0 and infinity, oops, sorry about that. I'm having a little issue with my recording right now. But as we take different values for that constant between 0 and infinity, oops. Sorry, Hayden. My computer's acting up a little bit. Hopefully it'll get itself under control soon. So we multiply this vector u by any positive constant, And if I multiplied it by 10, it's going to point in the same direction as you, but it's going to be 10 times as long. If I multiplied by 100, it would be 100 times as long. So as c takes on a range of values from 0 to infinity, we're going to get the rest of that line. We're going to get the entire line. Now, if c happens to be negative, let's say that c was -3. Well, then I would multiply each of the components of u by -3, and I would get this vector, -3, -6. To sketch that, I'll start at the origin. I'll go -3 units in the x direction and then -6 units in the y direction. I'm going to try to make my scale pretty consistent, although it's difficult to do. -3, -6 would sort of land me right there. That's approximately -3 times u. Notice that -3 times u is on the same line with u. All of these vectors have the same slope. If we look at rise over run, just, pre-calc style, right? They have the same slope. But when I multiply by the scalar, you can actually think of it as rescaling the vector. When we multiply by 2, we make it twice as long. When we multiply by 1/2, we make it half as long. We multiply by 3, it would make it 3 times as long. And anytime we multiply by a negative constant, it flips it in the other direction. So as c takes on an infinite range of values from -infinity to infinity, we actually get the whole line. So we can say that this line is a subspace. And that's a line with the following equation. It passes through the origin. So if we use y equals mx plus b, b would be 0 because b is where that line would cross through the origin. And the slope is found just using rise over run. We go up 2 and over 1. So this line given by y equals 2x is actually a subspace of the xy plane, or we could think of this as a subspace of 3-dimensional space if we wanted to. You can think of it as a subspace of R2, or if you're in 3-dimensional space, R3, or a subspace of Rn in general. So the span of a single vector is just what we get when we multiply that vector by a constant, but in general, it's just going to give us a line. Okay. Now, if instead of taking a span of a single vector, I take the span of 2 vectors, I actually get a plane. Let's say that the vector u is still the vector with components 1 and 2, and the vector v is a vector with components, let's say, let's just make it easy on ourselves. We'll say -2, say -2, +2. Now I want you to see what happens as we take linear combinations of 2 vectors. Here is the vector u. If we draw it in standard position, we start at the origin, go 1 unit in the x direction, 2 units in the y direction. That gives us the vector u. And then the vector v, if we draw it in standard position, requires us to go -2 units in the x direction from the origin and then go up 2 in the y direction. And that's our vector v. Now the span of these 2 vectors u and v is going to be it's going to turn out to be a plane. It's going to be the entire xy plane in this example. But let's say it's a set of all vectors w, such that w is some real constant times the first vector plus some real constant times the second vector. And what I want you to see is that that's actually going to give us all of R2, the entire xy plane. Again, thinking about what happens when we multiply u times c1, I guess I should make some statement about C1 and C2. C1 and C2 are real numbers. Okay. If I take U and I multiply it by any constant C1, that's just going to change the length of U. So if I wanted to, I could multiply U by the constant 2, and we get the vector with components 2 and 4. So we go 2 units in the x direction and 4 units in the y direction. Plot that point. That's the vector 2u. Oops, 2u, not 2b. Now, if I wanted to, I could take the vector v at the same time and multiply that by a constant. So let's take v and let's multiply it just by 1/2. We're going to take each component of v, multiply by 1/2. Half of -2 is -1. Half of 2 is 1. So this 1/2 of v is the vector with components -1, 1. So we're going to go -1 unit in the x direction, then 1 unit in the y direction. And this is not to scale. That should be pointed in the same direction but as v, but half as long. Now, if I'm talking about one member of this space, which is the span of these two vectors, u and v, I can take just any vector that is a linear combination of these two. So one vector in this space would be 2u plus 1/2 v. Now we can add these two vectors together in two different ways. We could add them algebraically or we can add them geometrically, but either way we're going to get the same result. Algebraically, this vector 2u is a vector with components 2 and 4. The vector 1/2 v is the vector with components -1, 1. And if we add those component by component, we have 2 plus -1 is 1, and 4 plus 1 is 5. So I claim, I'm just going to call this W, that W, the vector with components 1 and 5, is the same vector that I would get from adding this vector 2u to 1/2 of v tip to tail. Remember how that works. If I want to add 2u to 1/2 v, the first thing that I do is I draw 2u starting at the origin. And then I pick up where I left off. So I'm still here. And then I add 1/2 v. So 1/2 v is a vector with components -1 and 1. So this says wherever you are, go -1 units in the x direction and 1 unit in the y direction. So we're going to go back 1 and up 1 to 5. Okay. So I'm going back 1 from x equals 2 to y, or x equals 2 to x equals 1. Then I'm going to go up 1 to 5. Notice that this vector is parallel to this vector. So it means that that's the same vector. We can take a vector, we can pick it up, we can put it anywhere we want, calling it the same vector in linear algebra or in multivariable calculus. Either way is fine. Now, the resultant vector, whenever you add two vectors tip to tail, it's kind of like displacement, or you can think of like taking a flight with a layover. I can take a flight from here to here, and then I can take a flight from here to here, or I could just take a direct flight from here right to here. That is the vector W. So W, I need another color for W. W is this vector here. And one thing I want you to notice is that W has components 1, 5, because we go 1 unit in the x direction, 5 units in the y direction to get to the terminal point of W if we start at the origin. And that's exactly what we get here. If you're saying, what does this have to do with the span? I want you to think about like all the possible W's. Every possibility that you could get from taking a constant times the first vector and then a constant times the second vector and adding them together. Like W is just one possibility. Every time I take U and multiply by a constant, that's going to land me on this line. We're going to end up somewhere here on this line, given by y equals 2x, as we discussed. A constant times u, the set of all vectors that are given by a constant times u. Like that set, if we're just looking at sort of the terminal points of those vectors, we get that line. We get all of y equals 2x. Now we're going to take points on this line, and then we're going to add different vectors v. We could add v to this. If I wanted to add v rather than 1/2 of v, I would get this vector w, a different w. I guess I could call this one w1. I could call this one w2. Sounds like we're doing our taxes now. But as we take on all possible values for the C1, we get points on this line. And as we take on all possible values for C2, let's assume that C1 is 0, and we're just talking about all the multiples of V. Well, that would give us a whole bunch of points on this line over here. And I want you to think about all the possibilities. If I take some multiple of u and then I add a vector v, I get this vector. If I take some multiple of u over here and I add a vector multiple of v, I end up over here. Or I could take a positive constant, multiply it by u, and then a negative constant, multiply it by v. If I did that, this plus a vector that goes this way would give me a vector w that goes like this. Call that w3. But as we do that, we get the entire plane. Because imagine you're taking a vector that goes this way and a vector that goes this way, and then you get a vector. Or here you're taking a vector that goes this way and then a vector that runs this way parallel to this line, then we get a vector. Or we could take u and multiply it by a negative number and take v and multiply it by a negative number and then add those together. And then we would end up over here. Or we could take u and multiply it by a negative number and take v and multiply it by a positive number. And we could end up, whoops, should be parallel to v, sorry. We would end up over here. So as we take all the possible combinations of u and v, we get the entire plane. I hope that that makes sense. I don't know that this picture was particularly helpful, but you want to think of taking a vector and then adding, and then when you add vectors, add tip to tail, right? That as we do that, we're getting like every single possible point over here. If you're saying to yourself, well, how about this point, Miss Townsend? How could I possibly get that point? Well, I don't actually know what the constants would be, but I know that if I wanted to get to that location in the XY plane, I could take u, I could multiply it by just the right thing, so that I ended up right there. And then I could take a v and multiply it by just the right thing, so that I ended up there. And then this vector plus this vector would give me that location for any point in the plane. Since it's possible to end up at any point in the plane so that the vector w starts at the origin and goes over here. Since it's possible to do that, the span of these two vectors is all of a two-dimensional space. The entire xy plane is given by this linear combination of vectors u and v. Now, your question, so that's span. Now, when your question deals with three-dimensional space, so it says, find a basis for the indicated subspace of R3. Now, here's your definition from your textbook. It says, a basis is a finite set S of vectors. So we don't want an infinite set, we just want a list. And it's called a basis for the subspace V, and the subspace V is this plane, provided that the vectors in S are linearly independent. Linear independence, for our purposes, when you're talking about two vectors, it just means that they're not multiples of each other. U and 2u are linearly dependent because they go in the same direction. We don't want that. Sometimes we actually want a little variety. We want vectors that go in different directions. Maybe we want them to have something in common, but we want them to be unique, right? They have they go in different directions here. So we want them to be linearly independent. And then we want the vectors together to give us this plane. So when it says here that the vectors in S span V, that just means as we take all possible linear combinations of those vectors. And remember, linear combination just means you're going to multiply the vectors by constants and add them together. You're going to get this plane. Okay, so we need two linearly independent vectors, meaning vectors that are not multiples of each other, meaning if we looked at them in the plane, one would go in one direction, the other one would not be parallel to it, it would go in some other direction. And we want those vectors together to give us this particular plane. So that's the goal. Now that we understand our goal, and hopefully we understand a little bit more about what span means, we can try to find two vectors that will give us this plane. Now, just to give us a better sense of what's going on here, I want to sketch this plane for you. I can't really sketch it when it passes through the origin. So I'm just going to sketch a parallel plane. So this is x minus 2y plus 5z. That's the plane that we're interested in. That one passes through the origin. Just to get a sense of what's going on, I'm just going to sketch a parallel plane, which is going to look just like this. But I want to be able to see it in three-dimensional space. So I'm going to make that right-hand side equal to 10. Since this is 10 and that's 0, these are not the same plane, but this one is parallel to this one because they have the same normal vector. And we know that they have the same normal vector because the coefficients of x, y, and z are equal in both planes. That's a fact from Calculus 3. If you're saying to yourself, how do you know that that's a normal vector, Ms. Townsend? We can have a different conversation and I can make you a different video about normal vectors of planes. But I'm going to assume for right now that you remember from Calculus 3 that this plane and this plane have the same normal vector. They're just parallel to each other because that right-hand side is different. Now, if I want to visualize this parallel plane, it's going to look like this. I've chosen this constant to be positive so that I can draw the first octant portion of the plane where x, y, and z are all positive. Remember from Calc 3, the xy plane is down here. That's where z is equal to 0. The yz plane is back here and the xz plane is over here. So if I want to sketch this, one way that I can sketch this is to think about where this plane would intersect the x-axis, the y-axis, and the z-axis. And that's easy enough to do. Just set two of the variables equal to 0 and figure out what the third would have to be, provided that the right-hand side is 10. So if I set x and y equal to 0, then we'll have 5z equals 10. So that plane, this parallel plane, it's not this plane, it passes through the z-axis at z equals 2. So we can solve that for z pretty easily by dividing by 5. Or if x is 0 and z is 0, we actually get a negative y value here. Maybe I won't be able to sketch a first octant portion. When z and x are both 0, we get y is equal to -5. That actually means our plane crosses the y-axis over here at -5. And if we let y and z be equal to 0, we see that x would have to equal 10. Okay, so we can't actually draw the first octant portion of the plane. But we get a part of the plane that looks like this over here, where y is negative and z is positive and x is positive. But of course, that's just a little triangle, a triangular region. You want to imagine that plane is extending. It's actually going to extend a little bit out into this first octant. In the first octant, we would just see this line in the XZ plane that looks like this, but that plane would come out sort of at us. It's a little bit difficult to imagine. But the normal vector to that plane is the vector that's perpendicular to that, and it looks like this. It has a vector with components of 1, -2, and 5. So this says, start at any point on the plane, go 1 unit in the x direction, -2 units in the y direction, and up 5 units in the z direction. And that vector will be perpendicular to the entire plane. Okay, so that helps us visualize this plane, which is not the same as this plane, but I just moved it. I made this right-hand side equal to 10 so that we could see it. It's a little bit harder to see when everything passes through the origin. But this plane, our plane is like this, but it's just going to be like a couple of like sort of levels down. Since this is 10, we get this plane crossing the z-axis at z equals 2. If that were equal to 0, that plane would cross the z-axis at z equals 0. So the plane that we're interested in is actually has a very similar shape to this, but it passes through the origin. It passes through that point instead. This is our plane. And that's the parallel plane that made it easier for us to see kind of what's going on. They both have the same normal vector. That's what makes them parallel to each other. Okay. Now, when we think about span, when we think about or span or basis, we're trying to find vectors that are linearly independent that will span this set B. So we want two vectors that we can take linear combinations of. So multiply one vector by a constant, multiply the other vector by a constant, add them together, and get all of the points in that particular plane. It's very similar to what we did here. It turns out when I'm talking about two vectors in 2D, I will get all of the multiples of u plus all of the multiples of b. If I add those together, I get this entire plane, the entire xy plane. Here we're in 3D, so our vectors are going to be in 3D, but I want two vectors in this plane maybe this is my vector u and this is my vector v, so that they go in different directions. Then if I take all the combinations of this vector and this vector, thinking about adding multiples, like taking this one and multiplying by a constant, so we end up over here or over here, and then taking this vector and multiplying by a constant, and then adding them together so that we can get to every single point in this plane, like that's what we want. Of course, we're not interested in those two particular vectors because they're in a different plane. We want the same vectors, but like over here in our plane. So that's the idea. If we can find two vectors in the plane that are not parallel to each other, then we can find a basis for our plane over here. So you might be saying to yourself, okay, now I understand what the question is asking me. How do I actually find those vectors? Well, remember, those vectors have to have terminal points that satisfy the equation of this plane. So the only way a vector satisfies that equation is if I've got this vector 1 times x minus 3y plus 5z equals 0. Like I could think of that a little differently. I can think of that as a dot product of the normal vector with the vector with components x, y, and z. So this is 1, -2, 5 dotted with x, y, z. And we want that to be equal to 0 because this vector, the normal vector, and this vector, which could be the vector u or the vector v, we want those to be perpendicular to each other because that normal vector is perpendicular to every single vector in that plane. Okay, so that's where we're at. We just need two vectors like that, two vectors that are linearly independent from each other, that both of which you could take a dot product with the normal vector n and get 0. And you can really choose any x, y, and z you want. So I would choose maybe we want this dot product to be 0. So, and you don't want to choose 0, 0, 0 because that's not the vector that we're looking for. We want a non-zero vector that will give us this 0 over here. So maybe in order for everything to cancel, whoops, sorry about that. In order for this dot product to be 0, I might choose for x to be equal to 5 and y to be 0. If x is 5 and y is 0, substitute into this equation here. We'll have 5 minus 2 y, oops, sorry, substitute into that equation there. We'll have 5 minus 2 times 0 plus 5z equals 0. That gives us 5 plus 5z equals 0. So 5z would have to equal -5, or z is equal to -1. So that tells us that the vector with components x, y, z equals 5, 0, -1 is in that plane. And if you're saying, how do you know that it's in that plane? I know that it's in that plane because if I take the dot product of this with that, I get 0. Now I want to choose a different vector that is linearly independent from this one that will also give me a 0. And if you take the dot product, notice it works. 1 times 5 is 5, plus -2 times 0 is 0, plus 5 times -1 is -5. 5 plus 0 minus 5 is giving us the 0. So now you just want to choose different x and y so that the next vector that we choose is linearly independent from this first vector. I'll call this my vector u. Okay, in order for the second one to be linearly independent from the first, since I chose x equals 5 last time and y equals 0, it might be better to just choose x equals 0 this time. And then let's say that since the coefficients of y and z are -2 and 5, I'll choose y to equal 5. Now I know that that will give me a linearly independent vector. Watch, because see what happens. If we plug in x equals 0 and y equals 5 to this equation, we get x minus 2y plus 5z equals 0. If I substitute in 0 for x and 5 for y, I get this. So I have 5z equals 10. And if I divide both sides by 5, I get z equals 2. So that means our second vector is a vector with components 0, 5, and 2. That's v. Now, if I take any linear combination of these two, multiply this guy by a constant, multiply this guy by a constant, and add them together, I can get a point in that plane. So the span of u and v it's going to be the set of all vectors w, such that w is a constant times u plus a constant times v, where those constants are real constants. That is going to give us that plane. And if you're saying to yourself, how do you know that that's going to give us that plane? We could check by taking linear combinations of u and v. So let's look at w. It's equal to c times the vector with components 5, 0, and -1, plus c2 times the vector with components 0, 5, and 2. If we distribute, we get 5c, 0, and or 5c1, 0, and -c1 for that first vector. This is all the possible all the possible multiples of u. And then here, if we multiply by c2, we get this. this is all the possible multiples of v. Again, thinking about this line and then this line, and then thinking about adding vectors going here, so many units in the u direction and then so many units in the v direction, and adding them together, we get a point over there. Then when we add these vectors together, we add them component by component, we get 5c1 and then 5c2, and then the last one is 2c2 minus c1. And I claim that no matter what c1, c2, and c2 are, these, using these as our x, y, and z, these will satisfy the equation of that plane. If they do for any c1 or c2, then we're good to go. Then we know that we've actually created a set of, or we've actually found a set of two vectors that span that plane. And since they're not multiples of each other, we know that they form a basis for that plane. So let's substitute these into our equation. We had x minus 2y plus 5z equals 0. So we're going to replace the x with 5c1, replace the y with 5c2, and replace the z with 2c1 minus, or 2c2 minus c1. I didn't really give myself enough space there. But if we do the arithmetic now, distribute the 5 over there, you get 5c1 minus 5c1 is 0, and then negative 10c2 plus, or negative 10c2 plus 10c2 is equal to 0. So you actually do get the 0 that you're supposed to get on the right-hand side. Okay, so that's how we do that. Hayden, I hope that makes sense. I know that's a lot because we had to talk about a lot of different ideas, the idea of span, the idea of linear independence. But with linear independence, again, it's very simple for two vectors. If they're not multiples of each other, you're good to go. If there are three vectors, it's a little bit more complicated, but basically you just don't want any vectors that are redundant. You don't want any vectors that are already in the span of two of the three. That may be a topic for another video. So I hope that helps. Let me know if you have any questions about this, Hayden. Sorry about the weirdness with the video at the very beginning.